Right, so in addition to this yield strength, in addition to the elastic modulus that we just mentioned, there are lots of other mechanical properties that we can drive, and this is what we are going to explain over this example, like the modulus of elasticity or Young's modulus or elastic modulus, all are the same, which is E that we just mentioned. The stress at the proportional limit, also we need it in some application. The yield strength, which is sigma yield, as we explained, also we need it in some design, the design of the material for many engineering application or even for manufacturing methods. We should have an idea about this yield strength in addition to the ultimate tensile strength of the material, modulus of resilience, ductility, toughness of the material. So all of these mechanical properties, we can drive them and more from this stress strain curve that we drive based on the tensile test. To explain some of these mechanical properties and how we can drive them from the stress strain curve, let us consider this illustrative example of a simple tensile test material or for a cylindrical material specimen that is made of aluminum. So as we say that aluminum and its alloys, we are expecting that this is a material without yield bond phenomena. It means that we are expecting to have a smooth transition from the elastic to the plastic region. But anyway, this is a material sample that is made of a certain material type, having an original diameter of 0.05 inches. This is the standard diameter, but as I said, it is not necessary to stick to this standard diameter. We can change it. Even we can change the shape of the material sample, and we can still do a tensile test for this material, which is equivalent to 12.8 millimeter if we're already working in the metric system and unit system, and the gauge length or the original length of the sample is 2 inches, which is given by 50.8 millimeter if we decided to convert to the metric system is performant. It means that we prepared the material sample with these dimensions and we have done the test and we got some experimental results, and we need to explain this, use this experimental results to drive some of the mechanical properties of the material as already required here. The obtained data are presented over the following table, which is this table. So we drive this table. One of the things, even it is not necessary to obtain a figure from the computer that is connected to the machine. Simply we can provide, or this machine can provide, or the computer can give us an Excel sheet that include the force versus the amount of elongation that had been produced within this material. So this is the table that already given to us that we drive from the testing machine, and this table shows the load, the force in terms of Newton if we are working with the metric system, unit system, and the length. This is the new length of the sample as we increasing the force. So as you can see, initially the force was 0. So that's why initially the length that had been measured by the extensometer over the machine, it was 50.8. 50.8, it means that we still working with the original length of the sample. The length has not been changed yet. There is no elongation in the material sample. But up on increasing the force, if we increase the force at 7,330, we're gonna end up with an increase in the length. This is another new length of the material sample. This is the instantaneous new length up on increasing the force by this amount. If we measured the difference between the new length and the original length, we're gonna end up with the amount of elongation that had been produced within this material because of that force. As you can see, as we keep on increasing the force, the corresponding length, new length value is gonna keep on increasing. Remember that this is the new length. It is not the elongation. The elongation, it depends on the difference between the new length, which we can refer as Li. I stands for instantaneous length. And this is the load, Fi, which is the instantaneous force. So for every force, there is a corresponding new length value. If we divided the new length, negative the original length, the first length, this is the original length, L0. This is at instant 0. Initially, it was 50.8. If we subtracted 50.8 out of any one of these values, we're gonna end up with the corresponding value of the elongation that correspond to this applied load, instantaneous load, how much it is. These are the forces in the metric system, and these are the corresponding length values if we are working with the metric unit system. But if we are working with the American unit system, so the force should be in LPE, which is already bound force, which is already given by these values, and these are the corresponding values of the lengths in terms of inches if we decided to work with the American unit system. But anyway, they are equivalent. You will be given one of these two data, whatever in the American system or the international unit system. And from this data, you are required to do these things. One thing is to draw engineering stress versus engineering strain curve, which is the stress strain curve that we were explaining over this one. You are required to use this data to generate a figure similar to this one as a stress strain curve. This stress strain curve is known as engineering stress, engineering strain. So the question is why we are involving the word engineering? Why we mention engineering stress, engineering strain? Why didn't we say stress and strain versus strain curve? Why we had to add the engineering? It means that this indicates that there is another type of distress, which is non-engineering. So since we have engineering stress and engineering strain, it means that we should have another type or other types of stresses and strain, which will not be counted as engineering stresses or engineering strain. So in general, we do have engineering stress and true stress, and this is what we are going to discuss over the last slide here. So we do have true stress and we do have engineering stress. We do have true strain and we do have engineering strain. One of the things that you should understand, what is the difference between both? When we should use or when we are allowed to use engineering stress and engineering strain, and when we are allowed to use the true stress or true strain. This is another thing that you should understand, that definitely it will be explained to you. So it is required here in this example to draw, this is the first thing, to draw the stress strain curve, especially the engineering stress, engineering strain curve. Then from this curve or from the data that you already provided to you, your objective is to determine the elastic modulus of the material, which is E, and the stress at the proportional limit, the yield strength that we mentioned, sigma yield of this material, the ultimate tensile strength, modulus of elasticity, and the ductility, how much it is for this material sample. Make sense? So, starting with the engineering stress and engineering strain. What does it mean, engineering stress? It is simply the force divided by the original area of the material sample that is subjected to the force. So again, it is, mathematically speaking, engineering stress, it is the area, the force that acting over the material sample. Remember that you have a material sample with this form that is already has a cylindrical shape with an original diameter d0, which is already given to you. So simply we can calculate the original area as pi over 4 d0 square. The original diameter was given to us by 12.8 millimeter if we decided to work with the international unit system, 12.8 millimeter. So simply if you square the 12.8 square times pi over 4, you're going to end up with the original cross-sectional area of this material sample, which should be circular. And this material is subjected to a force, but this force has no one specific value, and instead it have multiple values. So we're going to add the subscript I here to indicating like this is if instantaneous. Like for the instant 0, the force was 0. For instant 1, which is F1 equals 7,330. For instant 2, it became 15,000 and something. For instant 3 or 4, it became 23,100 and so on. So for every instant of force of time, there is a certain value of the force. So that's why we're going to incorporate the I indicating the instantaneous force that we are talking about, to refer to the instant, at which instant is this force. If we divided all of these forces, every single force, by the original area of the material sample, this is going to give us the engineering stress. But the question is, intuitively, as we increase or stretch the material, what should be happen to the cross section, to the diameter of the material? Think of it like it is made of plastic. If you do have a piece of plastic and you're stretching this piece of plastic, definitely the length will be increasing, but the diameter is going to keep on decreasing till it will be completely fractured. And this can be clearly seen even within the necking point. Within the necking region, it became very thin till it will be completely fractured, right? So what does it mean? It means that as long the material, the length increases, the diameter of the material should be decreasing. Or at least it should be changing, whatever it is, increasing or decreasing. But as I said, and conventionally, it should be decreasing. So this means that for every force the area will not be constant. Because the diameter is going to change, it means that this area definitely is going to change. It means that for every single force, there is a corresponding cross-sectional area value. Why? Because the area is going to keep on changing, because the diameter is going to keep on decreasing as we are increasing the length of the material sample because of the force. But if we divide it over the original area, despite that, we all the time dividing by the original area. Why? But at this force, for example, the area, it is not the original area anymore. The original area, the true area, the exact area, it will not be the original area. It will be a new area, smaller one. If we divide it over the original area, this is going to give us the engineering stress. But if we divide it over the instantaneous area, the new area, this is going to give us the true stress. So what distinguishes, mathematically speaking, the true stress from engineering stress is the division, how you divide the force with respect to the original area or the instantaneous area. So for every instant of force, there is an instant of area or a new area. If you divide over the new area, this is going to give us the true stress. In some engineering application, we would need, or in some application, we would need to deal with the stress as a force over the instantaneous area, the new area. In some other application, we would need to deal with the stress as engineering stress, and in that case, we have to divide by the original area. Make sense? So in this case, here in this example, it is required to draw engineering stress versus engineering strain curve. It means that you have to divide every single force by the original area, which can be simply as pi over 4 the diameter square. This is the original cross-sectional area of the material sample. Also, how about the strain? The strain also could be true strain or engineering strain. The engineering strain, this is the material deformation in reference to its original shape or dimension. You should study in the mechanics of material class, especially for mechanical engineer, what does it mean strain, what does it mean stress, and what does it mean deformation, and what are the difference between the three perspectives or the three keywords. So strain, it can relate the deformation, which can be measured at the elongation. This deformation or a change in the shape or the length of the material sample, it is measured at the elongation delta L. We said that delta L, it could be the difference between the new length and the original length of the material sample, as already written here. Delta Li, which is the instantaneous elongation. Delta L, this is the elongation, equals Li, this is the new length, negative, or the instantaneous new length, negative the original length of the material. This is going to give us the instantaneous elongation of the material that correspond to this force Fi. If we divided this elongation over the original length of the material, this is going to give us the engineering strain at this instant of time. But in the true strain, and this is what basically why we are referring to the original length. Why didn't we refer to the new length? Because anyway, the length is going to keep on changing as we are increasing the force. If we decided to refer to the new length, in that case, we are introducing the true strain. And this is what distinguishes the true strain from the engineering strain. Mathematically speaking, the true strain is the ln, which is the natural logarithmic of the instantaneous length or the new length divided by the original length of the material. Here we are referring to the new length of the material. And if we draw the relation between the true stress and true strain, we should end up, this is what perfectly describes the plastic deformation of the material. And what perfectly describes the elastic deformation of the material is the engineering stress, engineering strain. So what does it mean? If we are using this material in any engineering application that require dealing with this material within its elastic region, the best way to deal or to represent the stress and the strain for this material in this application will be dependent on engineering stress, engineering strain, that we refer over the original area and the original length. But in some other application, we have to use the material within its plastic behavior. We need the plastic behavior of the material. In that case, we have to deal with the true stress, true strain behavior, true stress and true strain of the material that had been defined over the last slide. Make sense? This simply what distinguishes the engineering, whatever is stress or strain, or true stress or true strain. Here the objective in this example is to calculate this true stress, the engineering stress and engineering strain. How? This is the table. Your objective is just to prepare a similar table. These are the instants of time. For instant 0, the force was 0 and the length was original, 50.8 millimeter if you remember. Here we are working with the metric system. At instant 1, the force has been increased. At instant 2 has further increased and so on. So for these instant of time, this is like shots, like instant of time that had been recorded by the machine. And at this, in every instant of time, there is a force and there is a new length value as already shown here. So the first thing that you're gonna set up another column, that over this column you're gonna calculate the instantaneous elongation. This is the new elongation in the material. This elongation can be simply calculated as delta L as defined here equal the instantaneous length, the length at every instant, negative the original length. The original length, simply you're gonna find it over the first value in the column. So if you divided this at this instant, the length is 50.8 negative 50.8, which is the original length that is given to us, that we can simplify at the first row of this table. If you subtracted L0, which is 50.8 negative 50.8, this is definitely gonna give us 0, and that's why the elongation at the first instant it is still 0. Why? Because we didn't apply any force, and this makes sense. Then how about the second instant, or instant 1? We are gonna apply a force, so we're gonna end up with a new length of the material sample. If you subtracted this value negative the original length, which is 50.8, this is gonna give us the delta L1, which is the elongation at instant 1. This is instant 1 equals L1, which is the length at instant 1, negative L0. So 50.851 negative 50.8, this is gonna give us 0.051 millimeter as elongation at this instant 1. How about instant 2? Do the same. How about instant 10? At instant 10, this is the force, this is the new length. So if you subtracted the original length, 50.8, from the new length, which is 54.684, you're gonna end up with 4.0064 millimeter as elongation. This is gonna give you the 10th elongation, or the elongation at the instant number 10. Make sense? And so on, you're gonna keep till you finish the first row or the first column, with which is the elongation. Then you would need. So the other option, by the way, in some cases I could give you the force versus the elongation directly. So you're gonna skip this step. But here you already given the force versus the new length. So you have to form another column for the elongation. Then you're gonna work over the stress and the strain. Simply the engineering stress as defined, we should divide every force over the original area. So you're gonna calculate the original area once, which is gonna be pi over 4, the diameter square. Which diameter? The original diameter, before applying any force, which was given to us by 12.88. If you squared this value time pi over 4, you're gonna end up with 128.68 millimeter squared. This is gonna be the original area of this material sample. Then you're gonna divide every single force over this area. So 0 over this area, definitely this is gonna give us 0. So that's why at instant 0, the stress, it is still 0. But at instant 1, sigma 1 will be F1, which is 7,330 divided by this area. This is going to give us 56.1696. This is going to give us the stress. How about at the instant 10? You're going to divide the force over the same original area. For all of the forces, you're going to divide all the time over the original area, since we are seeking engineering stress. This is going to give us another value. If you divide F10, which is 47,300 divided by 128.68, this is going to give us 367.6, and this is going to give us the stress. How about the unit of the stress in that case? It will be in megapascal. So what does it mean, megapascal? Let us talk about the unit of the stress. The stress, simply, it is a force divided by an area. In the metric system, what should be the unit of the force? It is commonly known as Newton. So the Newton, this is the unit in the international unit system for a force. What should be the area of in the metric system or the international unit system. It could be in millimeter square, it could be in meter square, centimeter square, it's up to you. For example, if you define the force as millimeter square, and this is commonly what we are doing as mechanical engineer, if we divided Newton over millimeter square, this is going to give us the unit for the stress. It will be Newton over millimeter square. Very simple. This is equivalent to megapascal. But if you defined, the other option is, how about if you are interested in to define the stress in Newton as it is, but the area, it will be defined in meter square. So the stress definitely it will be as Newton over meter square. Newton over meter square is equivalent to Pascal. So the Pascal, it is Newton over meter square, but the megapascal, it is 10 to the power 6 Pascal, which is equivalent to Newton over millimeter square. So simply, if you already given this table, as the table is already given to us here, all the forces were given in Newton. So there is no need to do any unit conversion for the Newton, and all the dimensions were given in millimeter. The same thing, the cross-sectional area, the diameter was given in millimeter. So in that case, there is no need to do any unit conversion. Directly use the numbers as givens in the same unit system. So simply, if you divided the force by millimeter square, which is the area that we calculated as millimeter square, definitely any value that we get for the stress will be automatically in terms of megapascal. Make sense? So this is simply for the engineering stress. How about the engineering strain? As we define the engineering strain, it should be the instantaneous elongation that we just calculated here. We already set up this column. We found the values of the instantaneous elongation at every instant of time. If we divided this delta Li over the original length, which was already given here by 50.8, we're gonna end up with the strain. So simply the strain, your objective, like the first strain value at instant 0. The elongation is already 0. So if you divided delta L0 over L0, which is 0 over 50.8, this is going to give us 0. So that's why the strain at the first instant is 0. And this makes sense. Why? Because we didn't apply any force yet. How about the instant one? You're going to divide the elongation that you just calculated, 0.051, divided by 50.8. Remember that we all the time dividing by the original length, not the corresponding length. You should divide all the time by the original length, which is 50.8. This gonna give us the 1 point times 10 to the power negative 3. If you did the calculation, you're gonna end up with this value. So simply you can plug here 1 times 10 to the power negative 3. The other option that you can collect this 10 to the power negative 3 as a common factor. So if you plugged 1 here and you consider 10 to the power negative 3, for example, for the next steps, when you try to subtract any strain, you should remember that this strain is already multiplied times 10 to the power negative 3. Make sense? So this is going to give us the strain at instant 1. And do the same. How about the strain at instant 10? It's going to be the same. If you divided the delta L at this instant of time, which is 4.064, over the original length, which is 50.8, this is going to give us 80 times 10 to the power negative 3. Then since I'm considering the 10 to the power negative 3 as a common factor, I'm just going to plug here 80. It means that at this instant of time, the strain, it will be 80 times 10 to the power negative 3, which is going to be like around it's going to be equivalent to 0.08 as a strain. The question is, what is the unit of the strain? The strain, it should be dimensionless, has no unit. Why has no unit? Because the elongation simply, it is in millimeter, and the original length, it is in millimeter as well. So if you divide millimeter by millimeter, this definitely is going to give us 1, which indicates dimensionless. It means that has no unit. Okay, this is these are for the engineering stress and engineering strain. Then once we set up these two columns, you can simply draw them for every stress. So you're going to set up this figure. You're going to put over the horizontal axis. All the time the strain should be located over the horizontal axis and the stress over the vertical axis. Then in that case, you just gonna, for every corresponding strain value, the stress is 0. 0, 0. So you're gonna mark a point here. Then when the strain is 1, the stress was 56.96. So over the figure, you're gonna, at strain equal 1, you're gonna mark another point. And the strain equals 2, you're gonna mark another point, and so on. So you're gonna keep on marking and allocating these points. So this like form X and Y, like 2 points, like 2 coordinates of a point over the curve. Then if you connect this curve by hand, you're gonna end up with the stress strain curve, how it would look like. Okay, so this is known as the engineering strain curve, and this is the first requirement in this example. Make sense? Right, so once we drive this curve or draw this curve, how about if we are interested in driving some of the mechanical properties like modulus of elasticity and other mechanical properties from these curves? Let us start with the elastic modulus, or the Young's modulus, or the modulus of elasticity, or are the same definition of one term, of one material property, which is referred as E. As we defined before, this should be the slope of the linear stress-strain relation within the elastic region, which is already should be linear. So it means that simply if we can identify this linear line, this is the line. If we find the slope of this line, you can simply calculate the E from the curve. Also, we can derive this Young's modulus from the data that we prepared from the table. So you can, it's up to you. You can derive or find the elastic modulus from the table. Also, you can derive the elastic modulus from the curve. Simply from the curve, what we can do, you can simply draw a line that is considered to this straight line vertical, and if you allocate any triangular shape over it, draw any triangle between any two points over this line, and from this triangle you can find the slope of this angle theta. The slope of the angle theta, tan theta, is gonna give you directly E, the Young's modulus. The tangent of this angle, if we just decided to draw this triangle on a side here, this is the angle theta that I'm talking about, and this is the angle. So simply this value, it should be strain. This horizontal value, which it should be the strain difference between this point, because you're gonna plug a vertical point, a vertical line, another vertical line. The difference between the strains over these 2 points, this is gonna give you delta epsilon. And the difference between the stress, because if you draw a horizontal line here and another horizontal line, you're gonna choose the stress here and the stress there, and the difference between these two stresses, this is gonna give you delta sigma. So from the geometry of this triangle, if I ask you what should be the tangent of this angle theta, simply you're gonna say that it should be delta sigma over delta epsilon. This definitely is gonna give you the E, the Young's modulus. So this is how we can determine the elastic modulus from the figure. Draw any triangle, whatever it is, small or big. It should be bigger. It's going to be much more better. It's going to be bigger somehow. But anyway, you can draw any triangle that over this linear line that makes the hypotenuse of this triangle to be this straight line within the elastic region. If you found the slope of this angle theta, this is going to give you the Young's modulus or the elastic modulus. So be smart and don't increase the calculation over you or make it more complicated, because simply be smart and try to make use of these points that you already defined over the table. Like for example, I can draw a triangle between any of the 2 points, that located over the line, as I have done here. And also be smart more if you can consider that this triangle, for example, I can set up the triangle. As we mentioned, you can choose any triangular shape, form it over this line to calculate the Young's modulus, you're going to end up with the same value. So be smart and choose any one of these points. So initially, you're just going to draw a line to make sure which are the points that should be located to this line. So we do have this point, we do have this point, we do have this point in addition to this point. So choose any of these 2 points to set up a triangle between them and to do calculation for the elastic modulus from this triangle. So if I were you, I'm going to choose, for example, this point, and the other point is going to be 0. I'm all the time putting the 0 point as one of the 2 points. Why? To have because at this 0 point, how much of the strain it is 0, how much of the stress it is 0. So I already have these 2 values, 0 is already, to simplify the calculations. So I'm going to choose this point, for example, and draw a triangle vertical in this way. So this is gonna give me this red triangular shape. Then your objective is just to find the amount of stress that correspond and the strain that correspond to this point from this table. This point, if you count the point, this is point 1, point 0, this is the instant 0, instant 1, instant 2, instant 3. So the stress strain data at this point at instant 3 already given in the table. So at instant 3, the stress is with this value and the strain is with this value. Make sense? So this is the stress and the strain at this point. So simply I'm gonna use these two values, which are 179 point something, 0.52 as a stress, and the strain at this value, which is already 3, it is 3 times 10 to the negative 3. Don't forget the common factor, which is 10 to the power negative 3. This is gonna give us the strain. So simply from this triangle, I'm gonna calculate the stress as the difference in the stresses, delta sigma, which is the difference in the stress of this point and the stress of that point. So on the top here, I'm gonna put the stress of this point, which is 179.52 negative. The stress at this point, which is already 0, divided by the strain at this point, which is already the 3 times 10 to the power negative 3, negative the strain at this point, which is already 0. If you divided these two numbers together, you're going to end up with a value. This is going to give you the elastic modulus. Make sense? But the question is, what should be the unit of the elastic modulus? It should be the same unit as the stress. Why the stress? Because the strain has no unit. The strain, it is a dimensionless. So definitely the unit of the elastic modulus will be the same unit as the stress, which it could be megapascal, gigapascal, it depends. So, and this is what I have done here. This is how we can drive the elastic modulus from the figure, for a given figure. Draw a line, allocate any 2 points to set up a triangle, find the slope of this triangle, you're going to end up with the elastic modulus, as these are the calculations. So this will be the value of the elastic modulus as 59,840 megapascal. Why megapascal? Because we already using the same unit of the stress, which is already calculated as megapascal. If you divided this value by 1,000, you are going to convert the megapascal into gigapascal. So this is going to give us 59.84 gigapascal as elastic modulus of this material. Make sense? This is simply how we can drive it from the figure. But the question is, can we drive the elastic modulus from the table without drawing or generating the figure? Yes, we can. From this data, we can find an approximate value of the elastic modulus as what we have done here for the calculation based on the figure. How we can do so? Your objective. So as I mentioned, for example, if I give you this problem and I didn't ask you to draw the engineering stress, engineering strain curve, there is no need to waste time in generating and drawing this curve, and you can directly extract these mechanical properties from the table. So for every one of these mechanical properties, I'm going to explain to you how you can drive it from the figure. In the meanwhile, how about if you didn't draw the figure, can we drive it from the table? Yes, we can. I'm going to show you the two options how you can do this. So for example, for the elastic modulus from the table, so if we just cut this part, like so, I'm just this table here, this part is up to instant 5. So these are the data from this table, but just up to instant 5. So your objective here is just to observe the ratio between the stress over strain. So your objective is just to divide sigma over epsilon. This is sigma, which is the stress. This is epsilon, which is the strain. So if you divide it 0 over 0, this is going to give us an unknown value. So definitely you're going to skip this row. But now you're going to divide 56.96 divided by 1. This is going to give us 56.96. You can use the calculator very quick just to do this calculation. Divide this value of the stress by the strain. So like 117.34 divided by 2. So 170.34 divided by 2. This is going to give us 58.67. And do the same for the other points. And then your objective is just to observe the ratio. As you can see, the ratio here it is 56, here it is 58, almost the same. The difference is just 3. And here we do have 59, almost the same. And here we do have 59 point something, almost the same. So we're gonna end up like almost fixed relation between all of these values. But as you can see at this instant number 5, we're gonna start a change, another change. Like as you can see, the elastic modulus, it became kind of different. Like the slope, it became suddenly bigger difference. Like the difference, for example, for the first or 2 points, you can escape them, but try to observe more these other points. As you can see, the difference between 58.76 or 67 or 59.84 or 59.0625, there is no that much difference between these three values to consider that we have finished the elastic region. It means that all of these instant of time or all of these points still located within the elastic region. But for the instant 5 here, for the instant 5, as you can see, the stress-strain relation or the sigma over epsilon has started to change. And the change, it became significant. And as you divide more, for example, for the other points, like for instant 6, if you divide this value by this value, this is going to give us 29.8. 29.8. It is a very huge difference. It means that now we have moved to the plastic behavior of the material. And in that case, we can say, we can assume that the elastic modulus is going to be one of these three values is enough. It's fine. That is fine if you're going to choose any one of these three values to represent the elastic modulus of the material. Is going to be totally fine, and it's going to be very close to the value that we already detected based on the graphical method or from the stress-strain curve. One of the things, for example, that I used to do, I used to choose the elastic modulus at the last point that gave me almost the same slope, the same relation, the same value. So in that case, I'm going to choose the elastic modulus as 59.0625 gigapascal. This is going to give us the Young's modulus of this material. If you compare this one from the table to the one that we drive it from the figure, it is almost very close. It is typically the same like this point. But that is fine to choose any one of these 3 points or 3 values to be representative for the elastic modulus of the material. It is not necessary to be the exact value. We are estimating, we are finding the approximate value of this elastic modulus of the material based on this data or from the figure. Make sense? Another mechanical property that we can drive here is the proportional limit, which is defined as the stress at the end of the proportional or the linear stress-strain line within the elastic region. So simply this can be identified by drawing a straight line that is considered to the linear line in the curve and just observe what is the last point beyond which the curve will start to veer from this straight line. It will start to curve away from the straight line. So your objective is just to draw a straight line that is completely considered to the linear line. So as you can see, all of these points are considered to the line, up to this point. Beyond that point, as you can see, the curve of the stress-strain curve will start to veer from this vertical line or this straight line. This indicates that this last point will be considered or counted at the proportional limit, which is we can refer as P. The corresponding value of the stress that correspond to this proportional limit point is known as the proportional limit of this material, which is another material property that we could need it in some engineering application. We should have an idea about this proportional limit value or the stress that correspond to this proportional limit, how much it is. Make sense? So simply we can drive this thing from the figure in this way. As I mentioned, draw a line, just observe all the point, allocate the point that beyond which the line will start to veer from the line, and mark this point and draw a horizontal line that intersects with the vertical axis of the stress. Find the corresponding value of the stress. This is going to give you the proportional limit, which if we did so for this material is going to be around 230 36 megapascal. Why megapascal? Because the stress is already in megapascal and we already collecting a stress value that corresponds to this proportional limit point. This is how we can drive it from the figure. How we can drive this proportional limit from the table. We can do the same. Simply, we can determine this one at the last point. We can approximately determine this stress at the last point that over the last previous step for the calculation of the elastic modulus from the table. We calculated the slope of the stress over strain, and we end up with value. Then we define the stress, the elastic modulus at the last point that gives us almost the same slope. So this point will be counted. I can deal with it like it is. I can assume that this point, it is the proportional point based on this data from the table. And in that case, I'm going to say that this point 4 or this instant 4 is going to be considered at the proportional limit. And then your objective is just to find the amount of stress at this instant, which is 236.25 megapascal. This is going to give you the proportional limit of this material, how much it is. This is in case that you already using the data in the table, and the key condition is that this data should be smooth. What does it mean smooth? It means that this data should be lots of data. It means that you'd have so many points. In that case, from this table, we can use this approach to determine the same, almost the same value of the proportional limit. If we decided to subtract it from the table, similar if we have done this through the figure. Make sense? Another mechanical property here is the yield strength or the yield stress or the yield strength of the material, which definitely is going to be the stress value at the initiation of the plastic zone. This is the definition of the yield strength of the material. It is the amount of stress that initiates the plastic deformation. This is what distinguishes elastic from plastic deformation of the material. This takes place at the yield point of the material that start to experience the plastic deformation. As we explained before, the yield strength, we can easily identify this amount of stress for a material with a yield point phenomenon. This definitely you're going to have a proportional, this is the proportional limit, then you're going to have a sudden slight decrease. At the base, you're going to identify the yield strength of the material. So this is how we can identify the yield strength from the figure. The same thing here. I can simply do have like this material, then there is something is happening here. So we can simply identify the yield strength within this material. Kind of like this point is going to be the yield strength of the material. But as you can see, for this material, we do have a small transition from the elastic to the plastic region. So we have to apply the 0.2% of the length, original length of the material roll to identify the Young's modulus of this material. So your objective then is just to try to zoom and measure 0.002. Very small. You have to scale this. If you decided to subtract the Young's modulus from the figure, after you generate the figure, you're just going to measure 0.002 over the strain axis and mark a point. Then you're going to draw a very thin line that should be completely parallel to this elastic line that is going to intersect at a point. From that point, you're going to draw another horizontal line to collect the stress that correspond to this point. This stress is going to give you the sigma yield, which is the yield strength of the material. This is how we can drive it from the figure. So if we did so, if we draw a line at the 0.002 of the strain, draw a line parallel to the straight line, intersects with the curve in a point, mark a point, draw a horizontal line, then try to figure out how much is this value of the strain from the curve. If this is 200, and this is 300, it means that this dash in the middle, it should be 250. And as you can see, this point, it is somehow more close to the 300. So we can approximately determine this one as 280 megapascal is going to be the yield strength of this material from the figure, approximately. Other than that, you have to draw or to measure with a scale how much is this distance from the 250 to this point to identify exactly how much is the sigma yield exactly from the figure. Make sense? But anyway, it will be still counted or depending on the accuracy of generating this figure. So from the figure, we can determine the yield strength as 280 megapascal. Can we drive it from the table? Yes, we can drive it from the table as well. Subtracted from the table, we already identified the proportional limit. We identified the proportional limit at this instant of time. At this instant, it was identified, the point from the table for the proportional limit was defined at instant 4. So let us observe instant 4, 5, and 6. Like these three instants of time that we already have here over the table. 4, 5, and 6. So I've collected these. Let us collect these three rows and represent them here. Okay, so this is instant 4, 5, and 6. This is the strain and this is the stress. So the stress at instant 4 with this value, this at instant 5 and 6, this are the strain values at instant 4, 5, and 6. Make sense? And remember that this instant 4, this is the proportional limit, and this is the corresponding value of the proportional limit as 236.25 megapascal as we defined this value from the table. How about the yield strength from the table? So your objective is just to find the value of the strain at the proportional limit, which is 4. But remember that this is multiplied times 10 to the power negative 3. So 4 times 10 to the power negative 3, this is going to give us 0.004. It means that at this instant 4, which corresponds to the proportional limit, the amount of the strain is 0.004. Then, so we should expect the yield point somehow at a strain which can be approximately considered at the sum of this strain value plus 0.002. Why 0.002? Because we have to draw a line. We have to measure this distance. If we already given the figure, we have to measure this distance, then draw a line that is parallel. So if we are getting the proportional limit at this point, somehow we can approximate this distance at the 0.002. It is not exactly the same distance as this one. It could be bigger or smaller, but that is fine to approximate it with this value because we're still dealing with the small distances. So, and now we don't have the figure and we have to extract this data from the table. So this is a very good approximation. There is no need to do very accurate calculation how much it should be this distance, but that is fine if you just add it to the strain that it corresponds to the proportional limit 0.002. This is going to give us another value which it should be the strain at this point will be 0.006. It means that that is fine if we can approximately assume that the strain, the yield strength, is the stress at the 0.006 strain. So if you don't have this value of the strain within this table, no problem, you can get it directly. If you don't have, you have to do some interpolation between the two values. So for example, we agreed based on this approximation that the yield strength will be the stress at the strain equals 6 times 10 to the power negative 3. So the question is, why 6? Why we got it 6? Because we added 0.002 to the 0.004, which is the strain at the proportional limit. So we got this value. So let us find the stress corresponding to this strain value to this strain equals 6. This is going to give us the yield strength directly, approximately. It's going to be the yield strength of the material. Make sense? But do we have a strain equals 6 within this table? No. The strain we do have 4, we do have 5, then we do have 10. We don't have a 6 as a strain. So in that case, we have to do interpolation between the 5 and the 10 to find the stress that correspond to the strain 6, how much it is. How we can do the interpolation? It can be simply done using mathematics. The strain when it was 5, the stress was equal to 267.33, right? When it was 10, it was equal to 298.42. What should be then the stress when the strain equals 6? The stress at the strain equals 6, this definitely is going to give us the yield strength that we are seeking. So simply, we can determine this yield strength as by interpolation, if you just measure the difference between these two values, negative these two values, divided by this difference, it means that we can simply say that 6, negative 5 divided by 10 negative 5, this should equal to the difference between sigma y negative 267.33 divided by the 298.42 negative the 267.33. So we can end up with this relation. If we did cross multiplication, we can simply calculate sigma y, which should give us like around this value as 273 or another this value. As you can see, if you compare this yield strength to the one that we derive it from the figure, there is difference. This is 280 megapascal, but this one is around 273. So it is approximate value. Both are approximate value. These both are approximation, but this is how we derive from the table. This is how we derive from the figure in case that we already have the figure is already drawn. Make sense? So this is how we can calculate the yield strength, the proportional limit, and the Young's modulus for a certain material after the tensile test. Other property is the ultimate tensile strength or the ultimate tensile stress. So simply this is the maximum stress value at which the material will exhibit the necking, at which the material will initiate the necking behavior. Or this is the maximum stress that the material can withstand without fracture or before fracture. This is the ultimate tensile strength of the material. This is another mechanical property that definitely we are needing it or using this value for certain applications. It is simply the maximum value of the stress of engineering within the engineering stress strain curve. Like this is the curve. Your objective is just to choose the maximum stress value. If you draw a line that is horizontal that touches the curve from the top, the corresponding value of the stress, this gonna give you the sigma maximum, which is gonna be known as sigma u. In some cases we can write this one as ultimate tensile strength. ULT stands for ultimate, which means ultimate tensile strength of the material, or sigma u indicates also ultimate tensile strength of the material or stress of the material. So from the figure, this is how we can drive it. From the table, your objective is just to observe the maximum stress value within the table. But this mainly depends that you do have a decent table with enough amount of data points so you can choose the maximum stress value within this table is going to represent the ultimate tensile strength of the material. As you can see, the stress is going to keep on increasing up to this point, up to this value. Beyond this value, let's start to decrease. So we're going to say that this is the maximum stress value that we have, which directly will indicate the ultimate tensile strength of the material. So it is very simple how we can drive it from the table or the figure. Make sense? All right, so another property that we can drive from this stress strain curve is the resilience, which is known as the strain energy, also named as a strain energy, which can be defined as the capacity or the ability of the material to absorb and store. It is not just absorption, it is storing. It means that it's going to absorb the energy, then it's going to store this energy when it is deformed elastically. So this is the ability of the material to absorb and store energy while the material behaves elastically or within the elastic behavior of the material. There is no plasticity of the material in that case. This stored energy is used to restore the original shape of the material during the material unloading conditions. As we said that within the elastic region, when we apply a force, the material is going to deform. Upon the removal of the force, once you remove the force, the material will restore back again. How the material is going to restore back again by itself? This means any material to do any action, to do any response, to do any movement or deformation, it requires energy. So initially, we are giving energy through the work. We are applying a force. So we're already exerting energy. We are giving energy to the material to deform it. So this makes sense that the material is going to deform because of the force. But now we remove the force. Once we remove the force, the material restores back by itself. How? The material requires energy anyway to work. So this means that the amount of force, the amount of work, which would be counted as another form of energy that we give to the material to deform it, it has been absorbed by the material and is stored inside the material for a while. And then once we remove the force, the material gonna recall back again. It's gonna use this stored energy to reset back again to the original position or original shape. And this is typically what is happening in a spring. And this is how the spring is deforming and it can restore back. If you stretch the spring, it's going to increase the length. It's going to stretch with us. And this makes sense because we are applying force. But if we remove the force, the spring will reset back again by itself. How? It uses energy. What kind of energy? It is a stored energy, elastic energy, strain energy, or resilience that needed to return the material to its original shape one more time due to this stored energy that we're already giving to the material. So it is the ability. It means that the material or the spring had the ability to restore back because of this energy that has been absorbed and stored inside the material and has been used to restore it to the original shape and length. How we can measure it? We can measure the resilience of the material by a modulus known as the modulus of resilience, which is very similar kind of to the concept of the elastic modulus. It should be kind of related to the elastic modulus of the material. And this modulus of resilience can be defined as the strain energy per unit volume required to stress the material from the zero stress state up to yielding. In other words, it should be the energy divided by the unit volume of this material that needed to deform the material from the zero state to the yielding point. This is gonna give us the modulus of resilience, how much it is. We can simply calculate it by the UR, which stands for the modulus of resilience, equals the integration of the stress in relation to the strain over d epsilon from 0 to epsilon y. What is epsilon y? This is the strain at the yield point, or the yield strain, which at the yield point that we identified from this curve, this is the yield point at which we already calculated the yield strength of the material. If we draw a vertical line that intersect with the strain, this is gonna give us how much is epsilon y. This is the yield strain, how much it is. If we did integration to this relation between the sigma and the strain within the elastic region, and remember that within the elastic region, the stress should equal to the E times epsilon, right? So if you plug this relation into this integration, this is going to give us the integration from 0 to the epsilon yield of sigma, which is E times epsilon delta epsilon. Now, if you do the integration, remember E is constant. This elastic modulus is constant that we can simply move it outside the integration. So this is going to give us E times the integration of 0 to epsilon yield of epsilon delta epsilon. This is like the integration of x dx. You got my point? So the integration of epsilon is going to be E is constant. The integration of epsilon gives epsilon squared divided by 2. You're going to increase the exponent divided over the new exponent, and the limits of the integration are from 0 to epsilon y. So if you did the substitution, this is going to give us E times epsilon y squared divided by 2. This is going to give us how the modulus of resilience is calculated in terms of the elastic modulus and the strain at the yield point. In the meanwhile, what should be the yield strength of the material? The yield strength should equal to the elastic modulus times the strain at the yield point. Because we said, according to Hooke's law, sigma equals E times epsilon. So at any stress, there is a strain. At any strain, there is a specific stress value. So how much is the stress at the yield point is going to equal to the elastic modulus, which is constant at all points, times the strain at the yield point. So if we use this data and plug it here, we can simply determine the elastic modulus also in terms of the yield strength of the material as 1 over 2 sigma yield times epsilon yield. Sigma yield, which is the stress at the yield point. Epsilon yield, this is the strain at the yield point that you can determine from the figure or from the table. Or even if you decided to work with E and epsilon, yield is going to be E times epsilon yield squared over 2. even you can use Young's modulus in terms of sigma. So it will be the yield strength squared divided by 2 epsilon, 2E, which is the elastic modulus. So all of these three relations, I can write the modulus of resilience as E epsilon y square over 2. In the meanwhile, it is equal to 1 over 2 sigma yield epsilon yield. In the meanwhile, it is equal to sigma yield square over 2E. All of these relations are the same. They're gonna give the same exact value for the modulus of resilience of this material. So if we consider the definition of the modulus of resilience as half sigma times epsilon, this is gonna form over the stress strain curve. If this is the stress strain curve, and this is the elastic region, which it should be seen as a line. And this is the, at this point, the amount of stress is sigma y, and the amount of the strain, it should be epsilon y. So if we draw a triangle, this triangular area, and I ask you to calculate this area, how much it is. The area of any triangular shape, it should be equal to half the base, which is already epsilon y, times the height, which is sigma y. Very simple, right? Which gives us the modulus of resilience as already defined here. So what does it mean this? It means that also we can define the modulus of resilience at the area under the linear curve within the elastic stress strain relation of the material. As already shown here, it is this shaded area. If you calculated this area, this is gonna give you how much is the modulus of resilience, which we can simply calculate it using any one of these three relations depending on the given data. So from the figure, we can determine the modulus of resilience at the integration under the curve, or the calculation of this area. If you calculate this area, you're going to end up directly with the modulus of resilience, which can be simply calculated as 1 over 2 sigma y epsilon y, or sigma y squared over 2E. We already, over the previous steps, we determined the yield strength by 285. So you're going to square the value of the yield strength. And also we found the elastic modulus by 59.84 times 1000. This is just to convert from gigapascal to megapascal. So, and this definitely it is megapascal. So you have to make sure that the units are consistent. So that's why we already multiplying by 1000 over the value of the Young's modulus that we already got it. And this is the 2 that already found in this law or relation. If you substitute it, you're going to end up with 0.68 megapascal. Remember that this is a square. So that's why the unit here, it will be megapascal square dividing by megapascal. So you're going to cancel the square with the megapascal in the denominator. You're going to end up with megapascal as a unit for the modulus of resilience. Make sense? So this is simply how we can calculate it. Then we can convert it into a unit as energy per unit volume. So this means that the modulus of resilience, anyway, it can be, we can deal with it like it is a stress. But it's gonna be a fluid definition of the modulus of resilience, because the definition of modulus of resilience, it should be energy, strain energy per unit volume. So this indicates that the stress, this is another definition of the stress, that it is energy per unit volume of the material, like the modulus of resilience. So it means that we have to convert the megapascal into joule per meter cube, because the energy, it is measured in joules in the metric international unit system, and the volume, it is meter cube. So how we can convert? Simply you're gonna multiply this value times 10 to the power 6. This you're gonna convert it into the joule per meter cube. This is gonna give you the modulus of resilience, how much it is. That indicate how much of elasticity that could be stored inside this material and used to reset the material back to its original shape. Make sense? So this is one of the mechanical properties. Other one is the ductility. What is the definition of the ductility? You should have studied this in some other courses, especially for mechanical engineer. But ductility, simply we can define it as the ability of the material to deform without fracture. As you can see during the tensile test, we're gonna keep on stretching the material up to a certain point, it's going to fracture. So for example, if we decided to compare two different materials, and we extracted these two stress strain curve, like this blue curve indicate the stress strain curve for one material, and this red or brown curve indicate the stress strain curve for another material. So these are two different materials since we do have two different stress strain curves, indicating that absolutely these two materials are different. Which one is going to be considered as a ductile material? As I mentioned, the ductility, it means that this is a measure of how easy for this material to deform without fracture. To understand the ductility, let us compare the deformation of a rubber material. Like assume that you do have a plate like this one that is made of rubber, and the same plate made of glass. So if I ask you to bend the blade that is made of rubber, it will be bended with no problem. Even you're gonna keep on twisting and bending and deforming this plate of rubber with no deformation, with no fracture of the material, nothing wrong. Even once you put it on the table, it will be restored as it is. So we're gonna say that this rubber, it is very ductile material, has a very high ductility, kind of very flexible. But flexibility is kind of different than ductility, kind of. They are related, they are very related, but there is slight difference between them. So simply you could understand for now the ductility like it is very flexible material that can be easily deformed with no fraction. But the other side is the material that is brittle. Brittle material like you do have the same plate but made of glass. Since it is made of glass, and if I ask you to bend it, it will be completely fractured. It won't gonna be deformed. And instead it will have a fraction instantaneously as you try to bend this piece of glass. This indicating that this material has no ductility, zero ductility. This material with a no ductility is known as a brittle material. So this is what distinguishes the brittleness from the ductility, or brittle material from a ductile material. So a brittle material is the one that experiences very little deformation up to fracture. If you try to deform it, it will have a very small deformation, but instantaneously, very quick, it will be fractured. And this can be clearly seen from the figure. If you compare these two materials, the blue one, let us name this material A and this is material B. So material B, it can be highly deformed till it will be fractured. This is the fracture point as we explained over the stress strain curve or over the tensile test. So we're gonna keep on stretching the material, keep on stretching, and no problem, the material is gonna keep on stretching till it will be after a very high amount of strain. The strain here that the material experiences before fracture, it is huge in comparison to the material A. Material A, it will be slightly deformed, then it's going to be fractured. So if we decided to compare these two materials to each other, we're gonna say that material B is very ductile in comparison to material A. Or in other words, we can say that material A, it is very brittle in comparison to the material B, which is very ductile. Make sense? So ductility, how easy the material, the ability of the material to deform with no fracture, this indicates a ductility. So how we can measure it for a certain material? We can measure the ductility at the percent of elongation that the material is going to experience. Also, we can measure the ductility at the percent of reduction in the cross-sectional area. As we said, if you do have a bar or a material sample during the tensile test and this material is stretched, so the length will gonna keep on increasing. But what should be happen to the cross-sectional area? The area is gonna keep on decreasing. So if we measure the percent of elongation, the percent of increase in the length, this is gonna give us indication how easy, how ductile this material is. The same thing, if we measured the percent of decrease in the diameter, this also gonna give us an idea how ductile is this material based on the percent of reduction in the cross-sectional area. So these are two measures how we can identify the ductility of the material. So the percent of elongation, it can be calculated as the final length of the material before at the fracture, if since fracture. So this is the length of the sample of the material sample at fracture. Negative the original length divided by the original length times 100, since we are calculating a percent of increase, percent of elongation. This delta L, this L final or fracture, negative L0, this is gonna give us delta L, L negative L, this gives the elongation. So this is gonna be the elongation over the original length. and the elongation over the original length, this gives us the engineering strain as we defined it over the previous slides, right? So this indicates that directly we can calculate the percent of elongation at the final strain, or the strain at the last point, at the fracture point times 100. This is going to give us the percent of elongation, which gives indication about the ductility of this material. So this is the ductility of the material. It is measured by the percent of elongation. How can we determine this percent of elongation? We can determine from the figure at the fracture point. Your objective is just over this figure. Find where is the fracture point. This is the fracture point. If you drop vertical, you're gonna find the strain at this point. This is gonna be the final strain. If you multiply it by 1000, this is gonna give you the percent of elongation as a measure of the ductility of this material. Very simple from the figure. Can we derive it from the table? Yes. If you're gonna go to the table, choose the last instant that you have, which is this instant down here. At this instant, the amount of the strain, it is 165. So this amount of strain, this is the final strain. If you multiply it by 100, this is gonna give you how much is the elongation of this material. So if you multiply 165 times 10 to the power negative 3, because the strain, there is a common factor 10 to the power negative 3 times 100, this is gonna give you 16.5. which indicate that the percent of elongation as a measure of ductility of this material by 16.5%. Make sense? Also, we can measure it based on the percent of area reduction. So this is the calculation based on the elongation. It's gonna be the L at fraction negative original length over L0, which is gonna give us the 16.5% as I mentioned. Also, we can calculate it based on the percent of reduction in the cross-sectional area, which is gonna give approximate value or indication how much is this ductility of the material. So the percent of reduction is gonna be the original area negative the final area, or the area at fracture, divided by the original area times 100. How much is the original area? We already calculated it by over 4 d0 square, where d0, this is the original diameter of the material. But how about the final area? How much is the area at the last final stage of the material, at the last state at the fracture point? Something that we should understand of this material sample, that the volume of the material before the test and after the test, it should be the same. Why? Because nothing has been lost in this material because of anything. The material is still the same. The only thing that we have done in this material, we just stretched the material. So what does it mean this? It means that the volume is restored. The volume is preserved. The volume is still there. It is fixed. So if I ask you how much is the volume of this cylindrical shape before we do the tensile test, it should equal to the original area times the length, because it is a cylinder in a cylindrical shape. The volume of any cylindrical shape, it should equal to the cross-sectional area times the length of the cylinder, right? So it's going to be the same. So this is the area 0 times L0. This is the volume before the test. After the test is going to be the area at the fracture, or the final area after the test, times the length after the test, which should be the final length of elongated material sample. So simply, how much is the final area? The final area simply, it's gonna be, if you divide it by L final both sides, you're gonna end up that the area final equal to the original area, which we already calculated here by 128 point something. Over this step, we already calculated this original area here. So if we multiply the original area times the original length, which is already given to us by 50.8, divide this value by the final length, which is 59.182, you're gonna end up how much is the final area, and then you're gonna plug it into the percent of reduction to calculate how much is the percent of reduction of this material, indicating as a measure of the ductility of this material. Make sense? So if we have done this to the example that we have, this is the final area based on this calculation, the original area, which is this value times the original length divided by the final length. This is going to give us this value of the final area. If we plugged into this expression, we're going to end up with 14.16%. So the percent of elongation of the sample is 16.5%. The percent of reduction of the cross-sectional area is 14.16%. These two percents definitely they're gonna be different depending on the Poisson's ratio of the material, which is another mechanical property of the material that I'm going to explain. And this is some of the mechanical properties that you're gonna consider in some of the projects that have been proposed to you through this course. Make sense? So, for example, in some material, it is commonly known for mechanical engineering application, in case that the percent of elongation of the material, it is bigger than 5%, we're gonna count this material as a ductile material. But in case that the percent of elongation of the material it is less than 5%, we're gonna consider that this material is a brittle material. Make sense? So as you can see, this aluminum, it is a very ductile material. The percent of elongation it is 16.5%, which is way bigger than 5% as a limit between ductile or brittle material. This indicates that aluminum, it is a very ductile material. So what does it mean this? It means that you can handle a piece of aluminum and you can easily bend it and twist it and it won't gonna be fractured. And this is why we are making wires, electrical wires, for example, are made of aluminum, and we can easily bend aluminum without fracture. It won't gonna be fractured like the case of bending a glass. No, it is very ductile based on this data that already given here. Another mechanical property that we can drive, but we won't gonna calculate it for this figure because it requires lots of calculation, is toughness. Toughness, it is the ability of the material to withstand impact forces. This is in general, what does it mean? A tough material. Like you do have a material and you're gonna hit it with a very high force, impact force. Impact force, it is a force that is applied at an instant of time, then it will be removed, like hammering over the material. But pressure, for example, if you press over the table by your bare hand, and this pressure is gonna continue for a while, this indicates that this is a force, or a pressure, or a stress, which gradually and constantly applied over the material. But hitting over the material, this is impact. Like the forces had been applied over the material for an instant of time and suddenly removed. So it is a sudden force, like hammering or hitting a material. So this impact force, it has an effect higher, way bigger and higher than the conventional force, like pressing over the table. Make sense? So the ability of the material to withstand these impact forces without fracture, this indicates that this is a measure of the the toughness of the material. This is a tough material. Also, it can be measured at the ability of the material to absorb energy up to fracture. How much of energy that this material absorbed during the tensile test up till it will be completely fractured. This could be considered as a measure of the toughness of the material. So for example, if we're gonna compare these two materials, material A, the blue one, and material B with the reddish or the brown curve, which one it should be more tough? Material B has a higher toughness than material A. Why? Because it had absorbed more energy than material A up to the fraction. So this amount of energy that had been absorbed by this material B, it will be considered as the sum of the area under this curve till the fraction point. But the sum of the area of the blue curve up till the fraction point is somehow lower. If you calculated the area for material A and the area for material B, you're gonna find that the area under the curve for material B, it is bigger than the area under the curve of material A. This indicating that B, it is tough material, has higher toughness than the material A. Make sense? It is definitely somehow related to the ductility. So this expecting that a material that is ductile is more tough than the other material that is brittle. Why? Because the ductile material, it can absorb more energy without fracture more than the other material which is already brittle. So the ductility and brittle and toughness, they already somehow kind of related together. Make sense? So these are some of the important mechanical properties and how we can extract them from a tensile test for a certain material. But as you can see, all of these calculations depending on the engineering stress and engineering strain calculation within this table. And we said that the engineering stress and the engineering strain, they are different than the true stress and true strain. In some other application like manufacturing, for example, these engineering stress and engineering strain are acceptable, as I mentioned, as long as we are working within the elastic behavior of the material. And there are some other mechanical properties that we can drive, like toughness, ductility, and so on, based on this engineering stress and engineering strain properties of the material. But what is the true stress, true strain? It is a different measure that definitely we're going to use it, especially if we are interested in more details on the plastic deformation and behavior of the material in the plastic region. And this is what likely needed in some application of material science and some other application like manufacturing processing or manufacturing the material or the metal forming of the material. To change the shape of the material, we have to calculate or consider the true stress and true strain. We said that the difference between true stress and true strain is how you divide or drive the relation of the true stress. We said that the true stress, it is the instantaneous force divided by the instantaneous area, not the original area. The true strain, it will be the natural logarithmic of the instantaneous length divided by the original length. But there we are calculating the elongation divided by the original length. This is for the engineering strain. So the engineering stress strain curve declines after the material nicking. So after the nicking point, it goes down. Gives a wrong indication of the exact behavior of the material. Why? Because if I read this curve in that way, beyond the nicking, I'm going to say that the material becomes weak and it gets ready to fracture, as I mentioned before, right? But this is not an accurate representation of what is already happening in this material. Why? Because the engineering stress, it depended on we refer to the original area of the material. This would indicate that the material becomes weaker, where the stress decreases. Is gonna keep on the stress is gonna keep beyond the nicking point. The stress had been decreased, indicating that the material, it became weaker. But this is not necessary to be the condition for all the material. In some material, it could be even more stronger, despite that there is a nicking has been formed. This indicates that within the plastic region, especially within this region, the engineering stress and the engineering stress and the engineering strain curve, it is not that accurate to represent what exactly happening to this material. However, the true material strength in this region, it should be increasing in many of the cases, as I mentioned. This true strain can be detected if the applied force is divided by the instantaneous area of the material sample. Also, therefore, it is more meaningful to use the true stress, true strain curve when considering the material's plastic behavior than the engineering stress, engineering strain curve. Since we are interested in the plastic behavior of the material, the true stress, true strain curve is more accurate than the other engineering curve. Make sense? And this is how we can calculate the true stress and the true strain curve. And remember, in the meanwhile, you should understand that the volume is constant. This relation relates the true stress to the engineering stress. The sigma without any subscripts, this is the engineering stress. How it could be related to the true stress? It is going to be sigma times 1 plus epsilon, where this epsilon, this is the engineering strain, while this sigma, this is the engineering stress. So this is the relation between the true stress, true engineering stress. Also, the relation between the true strain, engineering strain is going to be epsilon true equal the length of 1 plus epsilon, where epsilon without any subscript indicates the engineering strain. Make sense? So this is what should be covered over chapter 6. The objective, as you can see, we focused over the tensile test. Why the tensile test? Because this is the most common test that from which we can derive so many mechanical properties of the materials. Make sense? So that's it for chapter 6, which was the objective of this chapter, just to discuss the mechanical properties of metals. And I hope things are clear to you, and thank you for watching, and see you in another video.